So in the last video, we discussed creating your own BlockMesh file for a simple cavity case. We had included a simple obstacle as well in this. Now let us take a step ahead and talk about using non-uniform mesh. In real life, when you work on complex problems, you don't have usually the liberty of using very fine uniform mesh everywhere. Based on your computational power, you will decide to allocate fine mesh in the areas of interest. For instance, in this case, if you remember what we were doing, it was a simple lid driven cavity. The top wall was moving at a certain velocity u. Because of that, obviously, at the walls, particularly this, and these walls, and because we have also included the obstacle and these four walls, we would be seeing formation of boundary layers. All right, and this will be more pronounced at higher Reynolds number. Remember, Re is equal to Vd by nu, based on the nu from the transport properties and the velocity that we are giving in the zero folder and the height of this cylinder over here or the obstacle here, we can calculate the Reynolds number for the flow. And the more this Reynolds number or the higher the Reynolds number, the pronounced influence or effect we would be seeing on the boundary layer, that it would thin a lot. And this thin boundary layer would not be captured by, a coarse mesh. No. We would require fine mesh there. And if you decide to use the same size of the mesh that you are going to, or the cells that are going to use here everywhere, it would cost a lot. The simulation would run for a very long time. Probably your system may get overwhelmed depending on your computing power. So obviously that is not a good choice, or that is not a good decision to make. What are the alternatives? The alternatives are that you, instead of using a uniform mesh everywhere, you create a non-uniform mesh, wherein you allocate finer mesh in the areas of interest and coarser elsewhere. For instance, in this case, we would require finer mesh near the obstacle and near the walls, these walls. That is what we are going to understand how to do. Now you must be looking at the stencil that I've drawn. It's very different from video number 2. The primary difference is that now I have drawn or divided each block that we had drawn earlier into, multiple blocks. And that is going to help us to generate non-uniform mesh. Let us see how. Let me open the case. So to save time, I have already, done the homework, in the sense I have created all the vertices, right? I got 36 points on the front, 36 points at the back, and I have already assigned them the divisions which we had before. Notice what I've done now. Earlier we had divided this whole thing into 20. This time I have split into 10 and 10, right? And if you see, when I run the BlockMesh, which Remember, we run over here zero constant and system. I've already run the block mesh, so let me show you the mesh. Uniform mesh everywhere. You will not realize where I have created the mesh or the blocks even. Now let us play. Remember, in our video number 1, I talked about simple grading and how we can play with these numbers so as to change the grading between the smallest size and the largest size of the cell, in the sense that we can now change the uniform mesh to a non-uniform mesh. How do we do that? Very simple. For that, or let us do a trial first so that you realize what I'm talking about. Yeah. So I change this. So say as an example to 10. And notice if I change in only one block and if I run block mesh, it throws an error. That point merge failure between the phase 3 and or of block 0 and phase 2 of block 2. 0 and 2. 0, 1, 2. So let me also define 10 over here and see what happens. Phase block 2 and block 10. Where is block 10? Block 10. So let me change here as well. Block 2 and block 10. Okay. 2, 3, 4, 5. Oh, my bad. This should be the block 10. Now block 10 and block 14. So 11, 12, 13 and 14. Block 14 and block 16. 14, 15 and 16. And now it has run. Let us check paraform. And now we see something different than before. The uniform mesh is no longer uniform. The cells are now crowded here and are sparse here. And if you remember the error that it had thrown before, the mesh connectivity issue. So if we have non-uniform mesh only in a certain block and uniform mesh in the other block, the cells cannot get connected, and that's the reason why it throws that error. We had changed the grading to 10. Let us change it to 0.1 and let's see what changes. Now the orientation has changed. So make a note to yourself, and that is that 0.1 or say less than 1, the grading makes non-uniform mesh run in this direction, in the sense the cells get crowded here and cores here, and greater than 1 the other way around. The similar logic applies to the y direction as well. Now why or what do I want here? As we have decided before, we want the fine mesh near the wall. So what I will do in fact is block mesh and paraform. That's correct. And now we need fine mesh around this wall. So that means I need to change something in the y direction. So let me do that and let me start again from this wall. So suppose I change this to again 10. So This time we do it here, right? Let me go. Run BlockMesh throws the error what? Block 1 and block 4. 0, 1, 2, 3, and 4. Block 4 and block 6. And 7. Done. Notice something different? Here, now we have made much finer. Now the same exercise will repeat. All right, and now we are starting to see continuity, so much so that you are not able to easily discriminate between the blocks. And now this is what we want. We want a relatively finer mesh around the cylinder, and we need finer mesh around the blocks. So now let us run the simulation. And let us open Parafoam. Beautiful. Let us plot the streamlines. Nice. So now you can observe that even with the non-uniform mesh, or in spite of the non-uniform mesh, we are getting better results, or the contours which are relatively smoother, finer than before, and obviously with less number of cells. I mean, and the kind of refinement that we have near the walls, if we have that throughout the mesh, the simulation would take much longer time. So I would say that we are looking at a very nice contour. And remember that we have a non-uniform mesh. Obviously have taken a very coarse mesh. This is not acceptable at all. We need we need to refine this even further, but this is an example. Now you must have noticed that I arbitrarily took 10.1 and all these numbers to make sure that you are doing the right way. What you can do is, in fact, use this calculator. If you just Google script OpenFOAM, you will be redirected to this page, or rather you can get the OpenFOAM wiki link of this page, and here you can use these drop downs and use these three options: that width of the start cell, width of the end cell, and total length. So for instance, in this case, as an example, all right, let us take the example of this cell over here. All right, let us take the example of this cell. So if we look at this cell, the length is 0.2 and this is also 0.2. Okay, so, and the number of regions that we have taken are 10. Say for instance, if we decide to divide it by 20 cross 20, then we can easily get the width of each cell, and then we can decide that what is the finest cell that we want. Say for instance, we decide the finest cell that we want is 0.01, and the coarsest cell that we want is maybe 0.1 as an example. Then we may enter that here 0.1. My bad. Here we'll enter the width of the start cell 0.01, the end is 0.1, and the total length is 0.2. So it will tell us you will have to use number of divisions 5, and the total expansion ratio would be 10. If you decide to go with a little finer division, something like this maybe, then it will give you the exact number of divisions that you'll have to use, 15, and the total expansion ratio 50 or 1 by 50, depending on the direction. So that is how you can use this calculator for deciding the grading with simple grading. All right. Now, what you can do is to challenge yourself. You can even divide, or go ahead and divide this in much smaller blocks, and give it a shot, wherein you will have a non-uniform mesh here, you'll have a non-uniform mesh in this region, and a uniform mesh in this region, so that you can even better control the level of refinement by using BlockMesh. Obviously, you can leverage any LLM tool, any GPT, for instance, and you'll be able to reproduce or write the BlockMesh file if you don't want to do it manually. But this will give you a better understanding of how mesh is generated, first of all, and second of all, how you can control where you want the fine mesh, the location of that, where you want the coarse mesh, and exactly of what size. That level of control, if you want, you can even go ahead and do this. All right, we'll stop here, and I hope I was able to convey it to you, the generation of block mesh with the non-uniformity, non-uniform mesh. uh, until next time, thank you.